Okay, so now that we have seen a little bit about the idea behind an RTOS, let's dive a little bit deeper into some generic concepts involving operating systems, and these are things that we need to understand in order to fully appreciate what exactly an RTOS does. So there are a few terms that we commonly come across which are worth sort of emphasizing and going over again. One of them is the so-called device driver, right? And what exactly do we mean by a device driver? A device driver, you can think of it as a set of functions that is provided to the user in order to interact with a given peripheral or an external device, right? So it helps you to interface with some specific hardware, and the whole idea is that you now provide generic functions at a higher level of abstraction than what would normally be used in order to communicate with the hardware. An example is shown on the right over here, right? So now don't worry about what this code actually does. It's just sort of a snippet of code taken from a possible driver that could be used on, let's say, the AVR series of microcontrollers. So each of these register names, right, the UBRR0H for example, is a macro name in some header file which is used in order to refer to a particular register inside the the AVR microcontroller. Each of these, right, the UCSR, these are probably some control status registers, UDR is some kind of a data register, right. So what is actually happening over here is that in order to actually communicate with the UART, you need to directly check the values of some of these peripherals, such as the RX enabled or TX enabled. You need to check what the values are. You need to also write certain values into the control status registers. You need to check whether a control status register has a certain value which indicates that the transmit buffer is empty or that it can accept new data. Similarly, you can check whether the receive buffer is not empty, and in turn get data from it, right. Writing code at that level where you are individually communicating with each register or each address inside the system is possible, but it is also quite painful. On the other hand, it's possible to write certain functions such as, for example, UART init, UART transmit, UART receive, and from there onwards this is sufficiently abstract that for a human being it's much easier to call a function like UART transmit and give it a character or a byte to transmit, rather than to actually write down each of these, the while loop followed by the assignment to the address and so on. Okay, so what this device driver has done is it has provided you with three functions. In this case, there is an initialization function, a transmit function, and a receive function. There will correspondingly be documentation which basically tells you that if you want to communicate with this device, use these functions in this manner. That at the end of the day is precisely the function of a device driver. It provides you with these functions that you can call, right. Now obviously the person writing the device driver needs to have very detailed knowledge of the specific hardware they are targeting, right. You need to know exactly how to transmit a byte in an AVR system, and similarly if you were writing a similar UART transmit function for STM32 microcontroller, you would have a different set of code for it. You would need to know things like the memory map of the system, the kind of register settings, everything. Every level of physical hardware level detail is needed in order to actually create the device driver. The advantage is once you have created the device driver, you can now move on to something called the HAL, the hardware abstraction layer, right. In the hardware abstraction layer, what we are trying to do is come up with slightly more generic abstractions, right. The functions at this level are also similar. They are still talking about a UART init, UART transmit and so on, and you might at first glance wonder, okay, what changed over here? Nothing specifically is different. I have just added HAL in front of each of those functions. The point is that there may be certain things like, for example, an initialization or a transmit capability which could be slightly different in different microcontrollers. What the HAL does is it abstracts that away for you and provides you with a standard set of functions, and it basically tells you that, okay, let's say that you are taking your driver and porting it to a new system. If you wanted to talk to the hardware abstraction layer, or if you want the hardware abstraction layer to be able to talk to your drivers or to your peripherals, you need to provide driver functionality that basically gives you that bridge between the HAL and the actual peripheral. So the HAL, in other words, wraps the code that you have for directly accessing the hardware. By itself, it is fairly generic, right? And what it does is it sort of establishes a set of ground rules or functions or baseline functions, which pretty much anybody after that can then build on and say, okay, these are the ways in which we are going to communicate with hardware. Right? At this point, as you can see, we are sort of 2 steps removed from the actual hardware. We don't need to worry about the direct registers, but we are in turn calling functions whose job is to actually know which registers need to be manipulated in which way. So the HAL or the hardware abstraction layer can be made sufficiently generic that it covers multiple different systems. Right? It is easier, at least. It's basically providing more abstraction for you to do so. And finally, we have the operating system, which builds on top of the HAL, right? And what the operating system does is it provides resource control. So let's say that you have a UART, the operating system needs to have some capability of saying that, look, there may be multiple tasks that need to transmit data on the UART. How do I make sure that at any given point in time, one of them is actually going to get access to the device? And how do I ensure that they don't sort of overlap with each other, right? And since we want operating systems to be as generic as possible, that is, we want them to run on many different kinds of hardware, what we do is usually build the operating system on top of the HAL. So the operating system in turn depends on the hardware abstraction layer. The hardware abstraction layer in turn depends on the drivers in order to provide the actual flexibility of writing the code. Now, with all of this in mind, it is very important to keep in mind that these are not rigid distinctions, right? Very often you will find operating systems directly talking to device drivers. You could have a system where there is no hardware abstraction layer. In fact, there is no operating system, and the end user directly writes code talking to device drivers. Or you could even have systems where people just completely ignore all of this and say, hey, I'm comfortable writing assembly language or directly manipulating registers. I don't need device drivers, right? And for that matter, it's even possible to have an operating system that directly talks to the underlying hardware without necessarily going through these abstraction layers that we talked about. So these abstractions are useful for us as humans to understand the layering, to understand the structure of such systems, and it also gives us a framework with which to think about such systems, right? But it's important to understand that they are not rigid distinctions, right? And they are only useful as long as they are giving you some utility, right? They actually help you to think about the system and to develop your code in a more clean and efficient manner. Now, all of those were generic to operating systems, but within the context of RTOS, there are a few terms that we need to sort of understand. One of them is the notion of a task. And a task is effectively an independent unit of execution. What does that mean? Practically, it will probably look like a function call in C. Right? So in order to execute a task, what I would do in my program would actually be more or less to call a function. Right? So why do we call it an independent unit of execution? That's because of the way that those functions are in turn called. Right? It turns out that, as we will see with examples later, what we finally want to do is the ability to call any one of those functions corresponding to a task in different orders at different points in time, so that overall these tasks can combine with each other in order to solve a larger problem. Now, just as each function has its own sort of register space as well as the stack memory associated with it, each task in a system also has its own state, its own registers, its own stack memory. In other words, the term that is usually used is its own context, right? So the word context over here and state in general have very similar meanings. It basically means what do I need to know in order to understand clearly what exactly a particular function or task or some part of my operating system is working on at the moment. Now, these tasks also tend to have certain states, the concept of different operational states associated with them. This is different from the because of this ambiguity in the terminology, the overall system state is usually called the context, which includes the overall memory, the register, stack and so on, and apart from that you have a so-called operational state associated with the task. The most obvious state that we can imagine would be that a task is running. In other words, the function has been called and you are actually running through the steps and executing some code. But as we will see, and this is where primarily tasks differ from functions, it is quite possible for a task to get blocked because it's, let's say, waiting for certain input or some other data to come from somewhere else, or for a resource to be freed up, right? And unlike a function call where pretty much we'll just wait over there and we don't really have any options on what to do, it turns out that in the case of tasks we actually have the ability to sort of suspend operation, go into a suspended state, and resume operation as and when the resource that we are looking for becomes free, right? So a task could be in a ready state where basically it's sort of running, but it's not doing any work, it's just waiting for something else to happen. In the context of what we have discussed earlier, it might be waiting for an event to wake it up and tell it what to do. It could be blocked, waiting for input. It could be suspended, which could be something directly done by the operating system, which basically just puts it to sleep for a while or suspends it so that it's not active at the moment, right? There are other possible states, and this is not sort of a a specific exhaustive list of possible states over here. Now, an analogy which sometimes helps in terms of understanding tasks would be, you have a factory and you have a number of different workers, each of whom has a different responsibility, right? So maybe they are all sort of controlling the construction of a car, and there might be one person who is responsible for the overall chassis assembly, another person for the wheels, another person for the drivetrain, right? And of course nowadays most of these would also be done by robotic systems, but there would be a person in charge of each of these. So these workers would essentially be executing individual tasks, and only by combining all of these tasks together does the overall task of actually building the car get done. Now what this means in turn is that when you have multiple tasks and you have a single processor on which these tasks need to run, you have another problem that comes up, which is called scheduling. Okay. Now scheduling essentially means that I need to figure out at what point in time each of these different tasks needs to run. So the bottom line is these tasks are executed or run on a processor, right? So the terms running a task or executing a task more or less mean the same thing in this context at least. And what it means is that I need time, I need clock cycles on the processor during which the instructions corresponding to this task actually get executed, and thereby some useful work gets done. So deciding on which task is going to execute next, if I have a single processor, right, and I sort of want to run multiple tasks on it in a time sliced manner, deciding which task goes next is basically the problem of scheduling. If I have multiple processors, I still might have more tasks than processors, which means I still have the same problem. It's just that it becomes a little bit more complicated, not less, right? Now in all of this, yet another problem comes in, which is to say that there might be certain tasks which demand high priority, right? You might want to say that, hey, this has to get done early, or it has to be done immediately, right? I can't wait for this, I need this task to be done immediately. The scheduler, in other words, has to decide which tasks go next, and not just decide that, it has to be based on some kind of priority that is assigned with each task. There are a number of different scheduling algorithms that are commonly used in every single operating system, not just in RTOS, but in RTOS in particular, the whole problem of scheduling has been very well studied, and there are usually fairly tight constraints on the kind of algorithms that can be used. This is something that we will not be getting into at all in this course. The terms are something that you might come across, but we will not be looking into the details of how scheduling algorithms work. Now once again, analogy. In the factory, there are multiple workers, each of whom needs access to certain devices, right? Maybe there's a screwdriver set, or maybe there's a particular scanner or something else that multiple people need to use, and the manager's job is to decide who gets access to which tool at which point in time so that they can finish their work. If ideally each of them is at their own workstation doing their work without interfering with each other, then that's great, right? The equivalent of that is when the number of tasks that you have is less than or equal to the number of processors that you have in the system. right? But the moment one worker depends on something that some other worker is doing, or two workers depend on the same piece of hardware in order to accomplish their work, the scheduler or the manager has to kick in and say, okay, now first you get to go on this, and then afterwards the next person goes. Okay, that's exactly the job that a scheduler is going to do inside an operating system as well. Now, as we saw over there, there is a notion of something called priority, right? Not all tasks are equally important. An example of that in the context of automobile systems would be the engine temperature control, right? Engine control in general, the engine control unit, with maybe subtasks being temperature control and monitoring, and the fuel mixture control, the overall various other kinds of things related to the operation of the engine, are going to be rated as very high priority, because if there is any deviation in the metrics that are being measured for those tasks, you can be sure that you need to respond to them immediately. On the other hand, there are certain other tasks, such as, for example, playing music, or the dashboard display, or responding when a person presses a button, corresponding to navigation, or well, navigation is important, but it's not split second important at the same level as what engine temperature control would be, right? Even if there is a few hundred milliseconds of delay in playing a song, for example, right, the user may not even notice it, and in most cases it's not life threatening in any case. So the point is that already we can imagine that there could be different tasks with different priorities, and one very important question that comes up in that context is, how do you decide the priority of a task, right? This is a very difficult problem in general, right? In some cases it's very obvious. For example, pressing the brakes is more important than switching the channel on the radio. But on the other hand, which is more important, pressing the brakes or controlling the temperature of the engine in order to avoid a potential explosion of the engine, right? Both are extremely critical, extremely important, and both need to be addressed very quickly. Okay, so deciding on priority levels itself is not a trivial task, right? And the second thing that can come up over there is the notion of so-called preemption. In other words, you could have tasks that actually, once they start, take a long time to run. And by long, we might even be talking just about milliseconds, right? It might be that if a task takes, let's say, 50 milliseconds to complete, for a human being that's nothing, for a computer that's ages, right? It might be that if I have not responded to a braking request within 50 milliseconds, I actually have trouble with the system, right? So in that context, we might have this notion of so-called preemption, where a high priority task is able to just stop a lower priority one and take over, and eventually the operating system in most cases would be able to come back and resume the lower priority task. Okay. And this becomes very important when you want to do efficient management of resources for a large system. And one other key concept in real-time operating systems is determinism, which basically says, first of all, can the outcome of a particular operation be predicted accurately? In other words, it's like saying, okay, whenever I press the brake, I should be able to guarantee that the car is going to slow down, right? So that's deterministic. I press the brake, I immediately expect the car to slow down. If I press the brake and the car ends up speeding up, for example, it means that something has gone wrong. It is not the behavior that I expect, and it is possible that due to some kind of non-deterministic behavior, which means that every time you run it, it's not the exact same thing that you're going to get, it is possible that something could go wrong, right? An example of non-determinism is something like rolling dice, right? Whenever I roll dice, I don't know which number is going to come up ahead of time, right? It could be any number from 1 to 6. But on the other hand, if I actually take a knife and cut through a slice of bread, I do expect it to cut exactly into 2 parts, right? So that is deterministic behavior. Non-deterministic behavior is all around us, right? It happens all the time, but in the context of a real-time operating system, it can be very problematic to handle. So if an operating system can sort of give you some kind of determinism guarantees for at least certain kinds of tasks, that if this is requested, this is certain to happen, that is a very useful sort of property. In fact, it's critical for the actual implementation of real-time systems, right, where you might have deadlines which, as I already mentioned, may not be very fast but are very specific, right. And if you do not meet those deadlines and if you do not sort of stick to the exact routine of operations that you have, other things could go wrong. A very interesting example of this, some of you may have seen videos of multiple robots working on a single car, right, and you might have noticed how it's almost like a dance, right. The different arms of the robots move around in such a way that they are actually swinging from one side of the vehicle to another, but they all ensure that they get the right path to the right place at the right point in time. And if you look carefully, you will notice that in terms of the paths that they are actually following, there could be points where they are actually cutting across the path that was earlier followed by another arm. What that means is, if you did not have absolute guarantees of determinism, it's entirely possible that two of the arms try to end up in the same place at the same time, causing a collision, right. But as long as you have absolute guarantees on the determinism, how long is it going to take for this arm to go from point A to point B? In other words, how long, at what point in time can you be sure that it would have cleared this particular space? Then you can schedule another arm to pass through that space at the same point in time without having a collision. So most RTOS provide some kind of features for providing this kind of determinism. Now there are a number of different examples of real-time operating systems. Those include commercial RTOS, some of the well-known ones are VxWorks, QNX, there is ThreadX from Microsoft, which is also used in some of the Infineon USB microcontrollers and so on. There are some open source RTOSs, one is called Zephyr, there is another one Chibios, and in addition to all of this, there are also extensions to the regular commercial operating systems, or not just commercial, right. Linux is open source. RT Linux is a set of extensions that provide certain kinds of real-time guarantees, basically the determinism and the time critical behavior capabilities for Linux based systems. Similarly, there is a Windows RT which can be used for taking Windows based systems and providing certain kinds of real-time guarantees on it, right. Now the point is that there are a large number of options to choose from. In the present instance, what we are going to do is take a few examples from a particular OS called FreeRTOS, right. That's sort of the vehicle that will, or the running example that we'll be using for most of the discussion as for the remaining part of this course, right. Now why FreeRTOS? Is it the best operating system? Is it because it is free? Yes, it is definitely because it is free. It means that we have access to the source code. You can actually understand how it works, right, and if necessary you can even improve upon it, right. That is the sense in which it is free, it is not necessarily the cost. But in our case, it turns out that yes, it is well enough documented and generally well supported and is available on sufficiently many systems that it makes sense to sort of consider it. Is it the most efficient? Possibly not. There are definitely reasons why the commercial systems exist. The kind of functionality and the kind of support that they provide are probably better, at least in some specific cases, than what can be got from a free operating system like FreeRTOS. But for our purposes, at least to understand what an RTOS is and to get started, this more than serves the requirements, and this is what we will be taking up as a running example.